Let's look now at section 15.1, and let's talk about vector fields. So just like any good section, we begin with a definition. All right. We're going to define a vector field. Usually I give some form of intuition first and then go into a definition and theorem. But here we're going to start off with the definition, and then we'll slowly explain aspects of the definition throughout the section. So we're going to begin with a region. Let R be a region in the plane. Okay. Let F be a vector-valued function of x and y. So here when we say the plane region, we mean the xy plane. So let f of x comma y be a vector-valued function. We've seen vector-valued functions before. You give me a number or a point, and I return to you a vector. All right? So let f of x comma y be a vector-valued function. Then F is called a vector field over R. The same thing can be said for a region in space. Instead of a planar region, we can take a solid region in space. So let Q be a solid region in space, not a skin, not a shell, but actually a solid region. The stuff on the outer edge, but also the stuff in between. So let Q be a solid region, and let f of x comma y comma z be a vector-valued function. Then F is called a vector field over Q. I suppose I should add something here. Let f of x comma y be a vector-valued function for points x, y in R. So let's go ahead and say that for x and y in R. Right? And same thing over here for x and y and z in Q. It may be that the vectors are defined for points outside of Q and for points outside of R, but we care about them specifically in this plane region and in this solid region. So here, let's consider an example of a vector field to help explain what it is that we're talking about. Let's take f of x comma y. So we're going to take something in a plane region. Let f of x comma y be given by the following vector field. And we're going to go ahead and sketch it because they say a picture's worth 1,000 words. And if we can see an illustration, it may help us explain what we mean by a vector field. So we're going to sketch the vector-valued function r of x comma y is given by y comma x. Okay, so here, if you give me a point x comma y, I'm going to give you back a vector where the first component of my vector will be that y, and the second component of that vector would be my x. Okay, something like that. So we're going to go ahead and sketch this thing, and let's begin with just a region in the plane on the xy plane. So let's go ahead and consider on the plane something like this. Okay. Now, one thing I could do is I could just start finding individual vectors and drawing them. That would not be the best idea, but we could do that. It would take an obscene amount of time to do it that way. So here I'm going to go ahead and do just one or two and see what that would look like. So here I'm going to say, okay, well look, here's a point on my region. It's 1, 1. All right. Okay, so at this point, I can create a vector. Okay, well that's going to be the vector. If this is the point 1 comma 1, well that will be the vector 1 comma 1. And the vector 1 comma 1 would point up and over, right? So something like this. Up 1 over 1. Okay? And I could do that for another point. I could say, for example, I want this right here. And this is the point 2, 0. So it would create the vector 0, 2. And I know how the vector 0, 2 works. It's going to start from this point, and it's going to go 2 units in this direction. Okay, something like that. So at this point, the point 1, 1 generates the vector 1, 1. And so I get the vector 1, 1, which I'll go ahead and assign to that point, starting from there, going that way. At this point, 2, 0, I generate the vector 0, 2, and the vector 0, 2. Oh, I have that backwards, don't I? 0, 2 would point upwards, wouldn't it? So it would look something like this. Okay. 0, 2 wouldn't go left or right, and it would go up by 2. All right, so obviously this is painfully slow to generate it this way. It could happen. It would be fine if you did this. It's just probably not something you want to do. Okay, so how would we want to do this? Well, let's consider the magnitude of these vectors. Here, we're going to go ahead and annotate that as the magnitude of the vector field, like this. Now, that may look a little strange, but basically all you're saying is, let's find the magnitude of an arbitrary vector. And we know how to find the magnitude of a vector. You're going to take the components, you're going to square them, you're going to add them together and take a square root. All right, so this is going to be the square root of, take your first component and square it, and then you're going to take your second component and you're going to square it, and you're going to add those together. All right? So this is just the magnitude of the arbitrary vector y comma x. Okay, so now what? Well, now consider a single magnitude, meaning pick a number and assign that as your magnitude. So here, I'm going to just arbitrarily choose a number. I'm going to just choose a simple number. I'm going to choose the number 1. So here, what I want to do is I want to find what are all of my points in my region, in my xy plane, that would generate a vector of magnitude 1. So what are all the points that generate a vector of magnitude 1? Which is just a matter of taking this expression and setting it equal to 1. So here we would say 1 equals the square root of y squared plus x squared. And then here we could go ahead and square both sides, and that would give us x squared plus y squared is equal to 1, which of course is a circle of radius 1. So what this means is that every point on this circle of radius 1 would give you a vector, when substituted into this vector valued function, which has a magnitude of 1. So now that we have something in common with all of these vectors, it'll be a little simpler to draw them all. So here, I'm going to go ahead and take just these 4 corner points here and map the vectors that come from them. Not that there's anything special about them, but they're a little bit simpler to draw. So here, if I use the point, what would this be, 1, 0, that would give me the vector 0, 1, which would go 1 unit straight up from there. All right, and then from here, this would be the point 0, 1, which would give us the vector 1, 0. So from here, this would go, let's see, which would give us this vector facing this way. Let's see now, if we have this point, which is -1, 0, that would give us the vector 0, -1, and 0, -1 would come on down this way. And finally, this point would be 0, -1, which would give us the point -1, 0, which would go in this direction here. Right? If we repeated that again for a different magnitude, we could say, what about magnitude 2? And of course here that would just be that this value here is equal to 2, which of course if we square both sides gives us the circle of radius 2. So what that's saying is that if every point on this circle gives us a vector of magnitude 1, then every point on this circle would give us a vector of radius 2, of magnitude 2. So here, if this is the point, well, actually we already have this one, don't we? So that would be this one. And then here, if this is the point 0, 2, that would lead to the vector 2, 0, which would be something like this. Here, this would lead, this negative 2, 0 would lead to the vector 0, negative 2, this one coming down this way. And this point 0, negative 2 would lead to the vector negative 2, 0, namely this vector going this way. Just like that. So even this simple and somewhat limited illustration shows us what we mean by a vector field. Essentially, on every point of your plane, you're assigning a vector. At this point, there's something that's causing a vector that is going in this direction, but not only is it giving you a direction, it's giving you a magnitude. If we were now to complete a vector for every point on this plane, we would get a very thorough illustration of a vector field. And since you likely don't want to sit there and watch me draw 100 lines, 100 little vectors, here's an illustration of what that's going to end up looking like. Notice that you have smaller vectors as you get toward the origin. Here you'd have vectors of magnitude 1 versus 2 versus 3 and 4 and so forth. Notice that as you're up here, your vectors are going toward the right. Down here they're going toward the left. Here they're going down. And here they're going up. And there's a pattern here in every direction. This is an illustration of a vector field. As you go further and further out, you have larger vectors. Here you have vectors going to the left, vectors going to the right. Here they're going up, and here they're going down. All right? So this is what our vector field would look like if we took the time to graph 100 little vectors. All right? One of the most common applications of a vector field is what's called a force field. A force field is exactly what it sounds like. It's a field over which you're applying a force. Here you would have, for example, the force of a magnet, saying, oh, if I'm at this point, the magnet is pulling me in this direction. If I'm at this point, it's pulling me in this direction. Force fields can be analyzing any action of any kind of force. You might have magnetic forces. You may have gravitational forces, or even the forces of wind. You might see something like this. This is somewhat of a joke, but it is actually an accurate representation of a vector field. Here you see the aerodynamic profile of a cow, which I'm not quite sure why I have this illustration, but I've had this for many years. And it serves as a wonderful example of a vector field. Here you have wind that is flowing. And at every point, there is a force on the air by the wind, right? That's what wind is. It's the moving of particles, pardon the pun there, the moving of particles of air that are either moving in a straight line or being deflected around a solid object. So here, the force which is moving that particle of air is going in this direction. Here, the force which is moving that particle of air is going in this direction. And here we have a somewhat silly, but an actual vector field, namely the field that tells you where each particle of air is moving and at what speed. All right. Let's go ahead and consider one more example. Let's do something in a solid region. Let's consider the vector field given by f of x comma y comma z equals to, and here this is very simple, x comma y comma z. So you give me a point and I'll tell you that the vector that is assigned to that point is the vector with the same components x, y, and z. All right. So again, drawing this would be possible, but very, very slow and very inefficient if we did it one point at a time. So generally what we want to do is we want to consider the magnitude of our vectors and then find all the vectors that have a common magnitude. And by grouping those together, it'll make things a little easier to visualize. So here the magnitude of this is x squared plus y squared plus z squared under a square root. Right? And so all vectors of magnitude 1 are at the points where this is equal to 1. Square root of x squared plus y squared plus z squared is equal to 1. Or squaring both sides, that's x squared plus y squared plus z squared is equal to 1 squared. Or in other words, just 1. Which we see is a sphere of radius 1. Centered at the origin. So here, if we were to draw this, we would say that every vector that is assigned to this sphere is of radius 1. Note here that if I have the point, here's x, y, and z. If I have the point 1, 0, 0, which is that point there, that's going to be assigned to the vector 1, 0, 0, which is pointing along the x-axis. If I have the point 0, 1, 0, that'll give me the vector 0, 1, 0. Right? They're all the same magnitude. They're all magnitude 1. We know that for sure. And here, if we have the point 0, 0, 1, that'll assign to us the vector 0, 0, 1. The same thing is true for the negative values. Here, if I have the point if I have the point negative 1, 0, 0, that would assign me the vector negative 1, 0, 0, going back toward the negative half of the x-axis. Here, this point, 0, negative 1, 0, would assign to me the vector 0, negative 1, 0. And the point 0, 0, negative 1, I would assign to that the vector 0, 0, negative 1. Just like that. So it looks like every point is going straight out from the pole, from the origin. Every point is simply taking the point on the sphere and pulling it out as completely perpendicular to the plane. That's not the right way to say that. Pulling it out directly away from the origin, not any kind of an angle here. If we do that for a sphere of radius 2, we notice that pattern persists. If we take x squared plus y squared plus z squared under a square root and set that equal to 2, well then that, once we square both sides, becomes the sphere of radius 2. That is centered at the origin. So if I now have a sphere of radius 2, then every point on that sphere is going to be assigned a vector, and that vector will also be of magnitude 2. All right? So here we're going to go ahead and take this point, which is 0, 1, 0. Oh, actually that would be 0, 2, 0, since it's on a sphere of radius 2. And so here this would be facing this way. It would be the vector 0, 2, 0, which would look just like this one, 0, 1, 0, except it would be twice as long. Something like this. And same thing for all of these. These would all face out this way. It would be a copy of what we had before, except now all the vectors are of a magnitude 2 as opposed to a magnitude 1. Here you can imagine sort of like an explosion. There's something in the middle that's propelling everything outwards. But here, the further something is away from the origin, the more force is being subjected to. So here the stuff in the middle is expanding slowly. The further out you go, the faster the object is expanding. All right, so this is another illustration of a vector field, this one in a solid region Q. Now, if you observe this one in particular, you'll notice that it has something in common with things that we saw in chapter 13. Namely, when we talk about the gradient of a function. When we talk about the gradient of a function, we're looking at the vector rather, that is perpendicular to the tangent plane. And that's really what that looks like, right? Here we have lines that are coming straight out from the surface of the sphere, which in a manner of speaking is, well, like saying these are gradient lines. After all, if I have the tangent plane here, that's tangent to this sphere of radius 2, then the line that's perpendicular to that one, the line that's normal to that plane, is exactly that red line. Same thing for all of these. If I have a tangent plane here that's tangent to that sphere of radius 1, this vector of radius 1 is normal to this plane here. So it almost looks like that is going to be a gradient. It looks like this vector would be the gradient of this sphere. You say, oh, well, maybe that's what vector fields are. Well, not necessarily, because after all, here that doesn't work that way. Here, if I take the line that's tangent to this curve, that vector is not normal to it. In fact, it's parallel to it. So it can be a gradient, but it doesn't have to be. It depends on the vector field. It's going to turn out that the vector fields that do behave like gradients are special enough for us to want to focus on. So this brings us to another definition. Let's talk about a conservative vector field. So definition. Let's start off with a vector field. Let f, and here I'm not going to put the number of dimensions because here it will actually apply to any number of dimensions. I won't put xy or xyz just to keep this generic. So let f be a vector field. If there exists a function, little f, this is not a vector field. This is just a regular function. Probably it's a multivariable function, but it's just a regular function the way we're used to. All right, f of x or f of xy or f of xyz. If there exists a function little f such that the gradient of that little f is equal to our vector field, then that vector field is called conservative. If that little f exists, it's called the potential function of our vector field. So we're defining the word conservative, and we're defining the phrase potential function. If you have some function whose gradient gives you that vector field, that won't always happen, but if you do, that function is called the potential function, and the resulting vector field is called a conservative field. All right, well, clearly that's not always going to be the case. In this illustration, we see that it is. We see, or at least we think we see that. The illustration implies that these vectors that are coming out of these spheres are the gradient of each of those spheres. But certainly that's not always going to be the case. You're not always going to have something that's normal to the tangent of your item, of your object. So how can we tell whether or not a vector field is conservative? This brings us to a theorem. As much as it pains me to say so, we're not going to prove this theorem just yet. The proof of this theorem requires something called Green's theorem, which we won't see until much later in the chapter. So here we're simply going to state this. Let's let m and n be the. Well, I suppose we should start with a region. So let R be an open disk. Okay. Let's take m and n to be functions that are defined on R, and we need them to have first partial derivatives. So let m of x comma y and n of x comma y be functions with continuous first partials. We can take their partial derivatives and we can note that they are continuous. On R, the field, finally let f of x comma y, let's let that be a vector field that's given by the vector m comma n. All right, so here this function tells you what the first component of your vector is. The second function tells you what the second component of your vector is. Then the theorem states that assuming all this stuff is true, f is conservative if and only if the mixed partial, so del n del x and del m del y are equal to each other. All right? Or in other words, if I take my first component and take the derivative with respect to the second variable, that should be the same as if I took the second component of my vector and took the derivative with respect to the first variable. If that's true, then your vector field is conservative. If that's not true, well, then it's not. Right? The proof of this is left until much later, toward the end of the chapter, because, well, frankly, there's some stuff that we need that we haven't really accessed yet. So here we're going to take advantage of the theorem and its results and worry about the proof later. So left for another time. All right. So here, let's just take a look at some examples instead. So as an example, consider the vector field on the plane that's given by the vectors 3x squared y squared, comma, 2x to the third y. Just like that. The question is, first of all, we're going to find if this is a conservative vector field. If it's not, well, then we're done. All right? So first find, so determine if f is conservative. If it's not, well, then we're done. If it is conservative, let's find the potential function. Because after all, that's what it means for a function to be conservative. It means that there is some function whose gradient is this vector field. All right. So first of all, let's go ahead and apply our test to see if it's conservative. Here, this is going to be our m. This is going to be our n. Let's go and label that. Here's m. Here's n. And what we want to do is we want to see, okay, the partial of n with respect to x and the partial of m with respect to y. All right, the partial of the first component with respect to the second variable and the partial of the second component with respect to the first variable. All right, let's see what that is. The partial of this with respect to x, well, this is the only variable, so you take your 3, bring it down. Subtract 1 from the power, and the y stays the y. Here, the partial of m with respect to y, okay, well here, this is a constant. This is variable, so take your 2, bring it down, and subtract 1 from the power. Notice that these two match. And because these two match, that implies that f is conservative. If they don't match, well then it's not. All right? Okay, so this is conservative. So now let's find our potential function. Okay, well in order to do that, we have to remember what it means for a function to have a gradient. Recall that the gradient of a function, the gradient of f, of x comma y, is equal to a vector where the first component is going to be the partial of f with respect to x at x comma y, and the second component is the partial of f with respect to y at x comma y. So what that means is that this is the partial with respect to x. Oh, sorry, this is the partial with respect to x of some function. We know that's true because it's conservative. this n will be the partial with respect to y of some function. Okay, so this is a partial derivative. So how do I find what function has a derivative that gives me this? I need to find an antiderivative. So here we're going to take the antiderivative of 3x squared, y squared, with respect to x. And we're going to take the antiderivative of the second component, that's going to be 2x to the third y, with respect to y. So assuming your function is conservative, you want to take the antiderivative of your first component with respect to x, because that's what you took a derivative of with respect to in the first place. And you want to take the second component and take its antiderivative with respect to y. Okay? In the end, our answer will be the union of these. So sometimes these will be exactly the same, but sometimes there will be a little difference between the two of them. In the end, the answer is the union. If there's one term that's in even one of these, it should be as part of our potential function. So here, let's take a look and see what this is. If we're taking the integral with respect to x, well, that's the only variable. So I would raise that power by 1 and then divide by the new power. So it would be 3. I would take x to the third over 3. And then since that's constant with respect to x, that just stays y squared plus a constant of integration. So here that's going to be x to the third y squared plus a constant. We're going to do the same thing to this one. We're going to go ahead and take the integral with respect to y. Okay, well that would be 2x to the third. That's constant, so that's going to stay by itself. Now we're going to leave y, and since that's a variable, we're going to raise that to the next power up and then divide by the new power. Notice those divide out, and so we get x to the third y squared plus a constant of integration. So here the union of these two, well, they're exactly the same. So the union is just that. So here our potential function is going to be given by x to the, let me write that as f of x comma y is equal x to the third y squared plus a constant of integration. If this had had an extra term, like for example plus x, and this one didn't, that extra plus x will be part of the potential function as well. In the end, you're going to take the union of these two sets of terms to give you your potential function. So yes, this is conservative, and here is its potential function. If ever you're not certain that you did that correctly, find the gradient of this, and it should give you back your original potential function. Oh, sorry, it should give you back your original vector field. Just like that. Note that this definition for a conservative vector field along with the test for a conservative vector field is only valid on a plane region. But of course we can define a gradient on a solid, on a function of 3 variables. So here let's go ahead and see what that looks like generalized to a higher number of variables. So So here's the theorem. And this is essentially the same theorem we just saw, but this one's going to be for a solid region. You're going to notice a lot of similarities. First, we're going to have a solid region, so we no longer have an open disk R. Now we have Q is an open sphere. So let Q be an open sphere. All right. Now we're going to need 3 components of 3 variables. So we're going to let M of x comma y comma z, N of x comma y comma z, and P of x comma y comma z. Let's let those be functions with continuous first partial derivatives in Q. Be functions with continuous first partial derivatives in Q. Okay. And finally, let's define a vector field. Let f of x comma y comma z be given by these 3 functions. The vector field is given by a vector whose first component is given by the function m, whose second component is given by the function n, and whose third component is given by the function p. Okay, so these are all of our conditions. We have an open sphere. We have three regular functions of three variables that have continuous first partials on that sphere, and we're defining a vector field of 3 dimensions by a vector whose components are given by these 3 functions. Assuming all of that is true, we can say f is conservative if and only if. Okay, so we still have one of our conditions was true. Del n del x equals del m del y. So notice this was the same requirement that we had for a conservative vector field in 2 dimensions here in on the plane. Del n del x equals del m del y. But now we have more functions that need to be compared. So we need for this to be true, and we also need for this to be true. We need a del p del x to equal del m del z, and we need del p del y to equal del n del z. Okay? If and only if all 3 of these are true. If these are all equal to each other, then that means that f is conservative. If any of them are not equal to each other, that means f is not conservative. Now you might ask, okay, so I guess I just memorize these, yeah? And of course that is one way. However, this shows up often enough that we have a separate notation for this, and it does help us to remember things. So here I'm going to hold off on giving an example of the theorem here for just a second, and let's go ahead and talk about the following definition. So we're going to begin with a function of 3 variables, just like over here. A vector field of 3 functions. So let f of x comma y comma z be a vector field given by 3 component functions: m of x comma y comma z, comma y n of x comma y comma z, comma p of x comma y comma z. Right. Then the curl. Oops, I misspelled a word with 4 letters. That takes some talent. The curl of the vector field f, which is usually denoted by the gradient operator here, by the differential operator, cross f. Here, this notation is meaningful. I'll go over this here in just a second. The curl of f, which is often denoted as the differential operator crossed f, the what now? Again, we'll go over this here in just a moment. That's going to equal to del p del y minus del n del z comma del m del z minus del p del x, comma del n del x minus del m del y. Okay. All right. This is the curl of f. All right. So if I take a vector field f, then the curl is some other vector given by these very complicated looking expressions. Now, one thing to note is that those two are these two. So if this is equal to that, that would make this 0, a number minus itself. Here, notice that those are those two right here. And in fact, if this is equal to this, then this minus itself would be 0. And notice that these two are these two expressions. So if these two are equal to each other, then that means that the difference between them would be 0. So here, when we say f is conservative if and only if this is true, we can also say if and only if, so aka also known as if and only if the curl of f is equal to 0, 0, 0. Okay, so that makes things a little easier to remember. Well, not really. Because here you're saying, okay, I can tell if a function is conservative, I can tell if a vector field is conservative if its curl is the 0 vector. Okay, I guess that is easier to remember, but then I have to remember what the curl is. And that's just as complicated as this was. In fact, identically so. Well, that's where this notation comes in. To calculate the curl of a vector field, this notation here, and I really should write that as a vector, this notation here is meaningful. It's a terrible abuse of notation. Technically, you should not be able to cross these things because this is a vector and this is a, well, it's definitely not a vector. It's an operation. This is an operation. It's like saying I'm taking a derivative or I'm taking an integral. Here, this is a terrible abuse of notation. This is equivalent to saying I'm going to take derivative plus 5 or something like that. I'm taking an operation times a number or a variable or a function or something like that. But even though this is an abuse of notation, it's a meaningful one. Here's what this means. This is the differential operator. And it's the symbol that we use to denote the gradient. Remember how you take the gradient of a function. You take the first partial with respect to x of the first component, the first partial with respect to y of to give you your second component, and the partial with respect to z to give you your third component. So here, this is going to be thought of as a vector. You say, well, the vector of what? Well, again, this is more abusive notation, but you can think of the differential operator as having 3 components. It's a partial with respect to x of something, a partial with respect to y of something, and a partial with respect to z of something. Now, normally we would say the gradient of f, the gradient of g, the gradient of h. So this would be del f del x, or del g del x, or del h del x. But here, by our abuse of notation, we're just going to consider this as if it were just the operations. Okay, so what? Well, that means that this notation can be thought of as this quote-unquote vector crossed with this vector, which in fact this one is legitimately a vector. So look what happens when you do that. If you take the differential operator crossed with your vector field, that's given by, at least in the notation, the partial with respect to x, the partial with respect to y, the partial with respect to z, crossed with m, comma, n, comma, p. Here I'm going to write it without the x, y, and z here, even though these are functions, just for the sake of simplicity. Okay, well, we know how to take the cross product of something. We write it this way. We have the I, the j, the k, the I, the j, and the k. Here, these are going to be my first vector components. So I'm going to write del x, del y, del z, and then I'll repeat that. Del x, del y, del z. And then these are the components of my second vector, mnp, mnp. All right, so now if I was going to take the cross product, and again, this is terrible abuse of notation. I know I keep saying this, but I feel like I have to. None of this is technically correct. You can't actually do this. This is meant as a mnemonic. It's meant to help you remember what this is without having to memorize something so difficult to memorize. Here, okay, that's going to be partial with respect, so it's I, partial with respect to y, p. So here we're going to write this as the partial of p with respect to y, I, We're going to write this one as plus the partial of m with respect to z, j. And then we're going to write this one as the partial with respect to x of n, k. So plus the partial with respect to x of n, k. Okay? And now we're going to go backwards. We're going to go this way. And that's going to give us the partial of n with respect to z, the partial of n with respect to z, and that's I. And then this one's going to be the partial of p with respect to x, partial of p with respect to x, and that's j. And then partial of m with respect to y, k. Partial of m with respect to y, k. And now remember how the cross product works. You're going to take that sum, and you're going to subtract. And you notice there's some terms you can combine. So in the end, you have that first component of your vector, right? You have a vector minus another vector. The first component of your vector will be this minus this. So that's going to be del p del y minus del n del z, comma, that's del m del z minus del p del x, del m del z minus del p del x, and that's going to be del n del x minus del m del y. But if you note, that's exactly what the curl is. That, and that. So once again, terrible abusive notation, but it works wonderfully as a mnemonic. You don't ever have to remember this definition if you just remember this notation and are willing to write it out this way. Now, of course, if you want to memorize that definition, that might actually be shorter, but that would take a very good memory, because here these are somewhat redundant and they're so similar it's easy to make a mistake. All right, so here's our theorem. It tells us that a vector field is conservative if and only if all of these equations are true, which can be condensed down to a simpler statement. A vector field is conservative if and only if its curl is 0. Okay, and how do you compute a curl? It's going to be the differential operator crossed with the vector field. I'll say it one more time. Terrible abusive notation, but it does give you a nice result. So here, let's take a look at an example of that. So here, let's consider the vector field f of 3 variables, f of x comma y comma z, to be given by z over y, comma negative xz over y squared, comma x over y, like this. The question is the same as before. Determine if f is conservative. If it's not, well, then you're done. If it is, find the potential function. Okay, so first of all, we need to test if this is conservative or not. So let's go ahead and find its curl. So is it conservative? All right, well, we can tell if we find the curl. I have no idea why. For many, many years I've taught this class. I screw up spelling the word curl a lot. I want to spell it C-U-L-R. I do it almost every time. Anyway, find the curl of f that's given by the differential operator crossed with your vector field. All right? Del cross f. Okay, well, that may be an abusive notation, but it's a very useful abusive notation. I, J, K, I, J, K. Okay? The differential operator is made up of del x, del y, del z, And same thing over here. And our vector field F is made up of those three components. So we'll just write those down. That's z over y, negative xz over y squared, and x over y. And same thing over here. Z over y, negative xz over y squared, and x over y. All right. So now let's just start computing some stuff. Here, we're going to take the partial of x over y with respect to y. In fact, let me just write that down. That's going to be the partial with respect to y of x over y. And that's I. This one is going to be the partial with respect to z of z over y. So it's going to be plus the partial with respect to z of z over y. Here, if you can do these in your head, there's no reason to write these down. If you know how to take that derivative, just do it. Same thing there, and same thing there. But since I have giving an explanation here, of course, I'm going to show more steps than people usually would. But here, if you can just take that derivative, just go ahead and do that. So here, this third one would be the partial with respect to x of minus xz over y squared. And that's going to be our k, minus, and now we're going to go backwards. We're going to go this way. And that's going to be the partial with respect to z of minus xz over y squared. I. That's going to be the partial of, with respect to z, of x over y. J. And that's going to be the partial, and that's going to be the partial with respect to y of z over y. K. Okay. So now we're going to find all these partials. Again, if you were just doing that in your head as you go through, take the partial, take the partial, take the partial, of course you would just write those down. But here I'm doing a little bit more than most people usually would to show each step. All right. So now we can go ahead and take those partials. And if I take the partial of x over y with respect to y, well, x is a constant, so it's really going to be the derivative of 1 over y, which is negative 1 over y squared, but then you multiply the x back in. So that'll give us negative x over y squared. That's your I. Plus, here the derivative with respect to z of z over y, well, that's going to give you 1. So you're just left with 1 over y. And that's your j. And then here the derivative with respect to x, okay, well that's just going to leave you all the rest of this. So that's negative z over y squared. And that's your k. Minus, and now we're going to take these derivatives. The partial of z with the partial of this with respect to z, well, that's going to go away, and that'll just leave you minus x over y squared. Okay. Here, the partial of x with respect to x over y, well, that's going to leave you 1 over y. J. And here, the partial with respect to y of z over y, well, the derivative with respect to y is just the derivative of 1 over y, which is negative 1 over y squared. But then multiply the constant z back in, so that'll give you negative z over y squared, k. And then when you combine your terms here, this minus itself, well, that's 0 for your first component. This minus itself, that's 0 for your second component. And this minus itself is 0 for your third component. So what that means is that when I compute the curl of f, I end up getting the 0 vector. And so yes, it is absolutely conservative. Whenever you have a vector field of 3 variables, if its curl is the 0 vector, it's conservative. If not, well then it's not. So yes, f is conservative. So now the second half of the question is to find the potential function. And this is going to mirror what we did in the previous one. Here, because this is the gradient of some function, this must be the partial with respect to x of that function. This must be the partial with respect to y of that function. And this must be the partial with respect to z of that function. So what we're going to do is we're going to take the antiderivatives with respect to those variables. So here we're going to take the antiderivative of z over y with respect to x. We're going to take the antiderivative of negative xz over y squared with respect to y. And we're going to take the antiderivative of x over y with respect to z. And in the end, we'll take the union of all of those. Right? If any of these have anything that's unique, it will also be included as part of our conservative function. All right, well, this integral is easy because that's a constant. And the integral of a constant with respect to x is that constant times x, plus a constant of integration. Here, same thing. With respect to z, this is a constant. And the integral of a constant dz is that constant times z, plus a constant of integration. And here, well, that's not constant with respect to y. So here, when we take the antiderivative of 1 over y squared, we would get, what would we get? We would get negative 1 over y. The negative with the negative would cancel, leaving us a positive 1 over y times xz. Or in other words, xz over y, plus a constant of integration. So here they're all the same. If this one had an extra plus x, or if this one had an extra plus y, or if this had an extra plus z, or whatever, if it had an extra something, then that would be included as part of your potential function. But here they're all exactly the same, so the potential function is just that function that we see repeated. So our potential function f of x comma y comma z is equal to xz over y plus a constant of integration. And if you have any doubts of that, you can always take the gradient of this, and it should give you that vector field again. Finally, for this section, we have seen a notation. The curl of f is given by, if you imagine this as being a vector crossed with this vector, then that is meaningful in some way. It gives us something. It's called the curl of f. Well, you know, if I'm considering this a vector, yeah, I could cross it with this, but there's another type of multiplication for vectors. What if I were to dot it with this? What if instead of a cross product, what if this was a dot product? Is that meaningful? Is that useful? Is there any reason to have that? It turns out yes. For this section, we're simply going to define it, and in later sections, we'll see it used. But this is called the divergence of f. So, definition. We're going to begin with a function, and we're going to define it simultaneously for 2 and for 3 variables. So, let's let f of x comma y, we'll start with 2 variables, be given by a vector m of x comma y, comma n of x comma y, just like that. Right? Then and let capital del give the differential operator, be the differential operator. Then the divergence of f, usually abbreviated as div of f of x comma y, is given by, and again our abusive notation is going to be the differential operator, but now instead of a cross is going to be dot the vector field f, and that's going to be given by the partial of m with respect to x plus the partial of n with respect to y. All right? And here the abusive notation is, here note, if you wrote this as del x comma del y, if you wrote that as a vector, and you wrote f as a vector, m comma n, then by our abuse of notation. Here, the dot product would simply be this with that one. Oh, that would be del m del x. And then this one with that one, del n del y. And then whenever you take a dot product, you take this, and then you take this, and then you add the two results together. So here, note, that's why we say that this is a dot product, right? Notice again, this is not true. Here, when you take a dot product, you multiply these and you multiply these. How do you multiply a function times an operation? That doesn't make any sense. But here, we use it as a mnemonic to remind ourselves, oh, these two go together, plus these two go together. Okay? Here, let me label that. That's called the divergence of f. We can define the divergence for something of a bigger space here. Let f be given as a vector field of 3 variables, something in solid space. And let's let that be given by m of x comma y comma z, comma n of x comma y comma z, comma p of x comma y comma z. And again, let the del be the differential operator. Then the divergence of f at x comma y comma z, well, it doesn't take much imagination. You're just going to add the third component. This is denoted as del dot f, which can be written out as del m del x plus del n del y plus del p del z, just like that. Okay. And again, this would also be the divergence of f, albeit for an f of 3 variables, for a vector field defined over 3 variables. Okay. A couple of notes on language here. Note, we've defined the curl and we've defined the divergence as being the differential operator multiplied by a vector field, and whether we use a dot product or a cross product, that's our difference. There are special cases when either the divergence or the curl are equal to 0. We've already seen what happens when the curl is equal to 0, and that's you have a conservative vector field. In later sections, we'll talk about the divergence and what that means. But here, a note on language. If the curl, yeah, I spelled it right this time. If the curl of f, which is again given by del cross f, if that's equal to the 0 vector, this is called an irrotational field. F is irrotational. If the divergence of f, which again is denoted as del dot f, is equal to 0, notice that wouldn't be a vector. The cross product is a vector. The dot product is a scalar, which again, that notation is a nice abusive notation to help us denote the difference. If the divergence of f is the 0 scalar, then f is said to be divergence free. Also sometimes called incompressible. At this point, you may have noticed a lot of language which is very, very suggestive. The curl. Curl sounds like something that should, well, curl up. Oop. I meant for that to be dramatic, but not that dramatic. Curl should mean something, curls up. Rotational, irrotational. That sounds like something should be spinning. What's curling? What's spinning? Divergence. Something should diverge. Something should grow or get big. Diverge, like a series. Incompressible. So that means something can be squeezed. So divergence, the curl, the divergence has something to do with things expanding or compressing. And conservative vector fields. What are we conserving? All of these names are very suggestive. That's because most of these things come from not from mathematics, but from physics. We develop them in mathematics because, well, that's where they're going to be developed. But the ideas that eventually became these operations come from physics. Throughout the sections and by the end of the chapter, a lot of these languages, a lot of these notations, a lot of this language will make sense. The curl actually does mean what it sounds like in a way. It has to do with rotations and things curling around and moving around. Divergence and compression has something to do with things expanding and contracting. And a conservative vector field conserves something. And all of these words actually mean something. So pay attention to the language, and in a lot of ways it'll save you from having to memorize some stuff by saying, oh, well, the name tells me what it does. For now, we've only learned what the definitions are, not exactly how they tie to the physical world, but that'll come in the following sections. But for now, as our last example, let's just give a quick example of divergence. Here, find the divergence of the vector field that's given by three variables. So that's going to be something in space, which is given by the vector x squared z, comma, negative 2xz, comma, yz, and here at a point 2, comma, 1, comma, 2, comma, negative 1, comma, 3. All right. So here, the notation tells us exactly what to do. The divergence, that's going to be, well, the differential operator, del x, comma, del y, comma, del z, dot our vector field, x squared z, comma, negative 2xz, comma, yz. And so here, the way we do a dot product, these two go together. So it's going to be the partial with respect to x of x squared z, which is 2xz, comma, oh, not comma, plus, these two go together. So it's going to be the partial with respect to y of something that doesn't have a y in it. Oh, so it's going to be the partial with respect to y of a constant, which is just going to be 0. Plus, here the partial with respect to z of yz. Okay, well, that's just going to be y. Okay, so here is our divergence. It's going to be 2xz plus y. And here they're asking for the divergence at a particular point. For right now, we're not investigating what that means, the application. Right now, we just want to make sure we can do these operations. In later sections, we'll see exactly what these are used for. And here, we're asking for it at a particular point. So we're just substituting in. That's going to be 2 times our x times our z plus our value of y, which is 12 plus a negative 1, which will give us 11. And finally, one last theorem, which almost seems unnecessary. Later on, it'll turn out to be a really rather useful result because of how simple the result is. So here, this one's given without proof, although this one, actually, you could prove it yourselves. If anyone who's interested in following mathematics beyond Cal 3 into linear algebra, proofs are a big part of that course, so you might actually consider trying to prove this one yourself. We're going to begin with a vector field, let f, and this must be defined over 3 variables, because here we're going to talk about a curl. Notice a curl is defined as a cross product, and cross products are only defined for vectors of 3 variables. So here, this must be in 3 variables. Note that we never defined a curl for something of 2 variables or 4 variables, because curls are defined as a cross product, which must be over 3 variables. We don't have a definition for them otherwise. So let f of x comma y comma z be given by m comma n comma p, where again m, n, and p are functions of x, y, and z. Let's let that be a vector field. And we want m, n, and p to have second derivatives, where m, n, and p, they actually need to have continuous second derivatives. So have continuous second partial derivatives. If that's the case, then the divergence of the curl of f, which is the same, is going to be just 0. The proof of this one is easily accessible, although a bit long. You have the definition of the curl of f. You can either use the mnemonic or you can just use the definition outright, but either way, we know the curl of f is given by this, right? There's the curl of f. Okay, now take that curl and take its divergence, and that is to say, take the derivative with respect to x, the derivative with respect to y, the derivative with respect to z, and you'll quickly see what happens. Well, maybe not quickly. Like I said, this one is not difficult, but it does take a bit of effort to go through the different steps here. So here, the proof of this, I've always wanted to say this, the proof of this is left to the student. It's not a requirement, it's not a homework or anything, but I would encourage you to try it. If nothing else, it'll give you a good idea as to how these interact with each other, and it'll give you a good handle of how this works as a vector and how this works as an operation on a vector. So you might consider trying that. And this will come back up at a somewhat unexpected time later in the future. The divergence of a curl will be 0, and that'll simplify some stuff wonderfully later on down the line. But for now, there's your theorem. And that's it for the section. As an assignment, you may wish to try from section 15.1, problems 19 through 47 every other odd. That sounds like a lot, but you're only doing every fourth problem. 51 through 63, again, every other odd. And then try 69 through 75 odd. Go through as many of those as your conscience will allow. If anybody has any questions, comments, problems, make a note of those and reach out to me, and I'll help you with what I can. All right? And I hope everyone has a nice day.